Math 2415, Chapter 10, Vectors in the Geometry of Space, Section 2, Vectors, Video 6, Vector Addition and Scalar Multiplication in Component Form. Now, there's a good chance you already know how to do this, and even if you don't, you probably have some intuition. But I want to give you the reasoning behind the intuition. And to verify this, let's just say I asked you, we'll get to this generic approach in a second, to take the vector 3, 2 and add it to the vector 4, 1. You probably already know how to add these because your intuition would probably tell you to do something and it would be correct. So I want you to think about how you would add those two vectors, and then we'll actually verify that what you think you should do, or what you probably think you should do, is correct. But let's take a look at the generic approach for a second. If you'll notice, I've got two vectors set up here, A and B, and I've already got them tip to tail because we're going to find the sum. In fact, the sum is going to run from the initial point to the second terminal point. Let me get my ruler, or rather my triangle. And if you notice, I also put A in standard position in the sense that it originated from the origin, or I should say initiated from the origin. So using the tip to tail approach, this is the vector A plus B. But let's think about what it would be in terms of components. Now, if you notice over here, I've generically represented both A and B in component form. Vector A as A1, A2, vector B as B1, B2. And remember, the components in component form represent the displacement in the horizontal and vertical directions, or I should say the X and the Y directions. So specifically, the A1 means that for vector A, I would travel A1 horizontally and then A2 vertically to get to its terminal point. And the same thing for B1, for vector B. I would travel B1 horizontally and B2 vertically to get from the initial point of B to its terminal point. But how would I represent vector A plus B in component form? Well, I would need to know how far to travel horizontally and how far to travel vertically. Well, that's pretty easy to see. If I take this B1 displacement and just translate it down to the x-axis, and I took this A2 displacement and translated it over here, I now have the displacements for the sum, the horizontal and the vertical displacement. Well, the horizontal displacement is just the sum of A1 and B1. Meaning that the first component of A plus B is just A1 plus B1. Excuse me. And similarly, the second component of the sum is just the vertical displacement, which is just the sum of the two vertical displacements of the original vectors, A2 plus B2. So to add two vectors, you just add corresponding components. If you were thinking that the sum of these two vectors was 7, 3, you were correct. Because 7 is the sum of the first components and 3 is the sum of the second components. I just wanted to give the geometric reason why we add vectors the way that we do. We don't just do it because it's easy and intuitive. We do it because it's correct in terms of displacements and how we illustrate the sum of two vectors. Now, if this were in 3 dimensions, it would be the exact same thing. We would just add the third components. And the same thing if you want to go beyond 3 dimensions. So adding vectors component-wise is crazy easy. You just add corresponding components. In general, you could say that if vector A is equal to A1, A2, AN, however many dimensions you want, and vector B is equal to B1, B2, Bn, same dimensions. You can only add vectors in the same dimensions, by the way. Then A plus B is equal to A1 plus B1, A2 plus B2, An plus Bn. In other words, vector addition occurs component-wise. You add corresponding components. Not a real revelation there. There's a good chance that you already knew that, but there's the geometric reason why, at least in 2 dimensions. Now, we've already mentioned scalar multiplication in the previous video, when I said that I had rearranged the videos to talk about unit vectors a little bit early, because we hadn't talked about scalar multiplication yet. But without much brouhaha, if vector A is equal to, and let's take this to any number of dimensions, A1, A2, AN. Now we'll only be dealing with 2 and 3 dimensions, but the idea extends beyond that. If vector A has the component form A1 through AN, and C is a scalar, then the scalar multiple C of A is just C times each component. CA1, comma CA2, comma comma CAN. Looks a little distributive. It's not quite distributive because there's not 2 operations going on here, but everybody gets the scalar. So scalar multiplication is, I don't want to say it's trivial, but it's pretty straightforward. Make sure I'm not leaving anything out here. Okay. Oh, I was just looking in the book and they do talk about n-dimensional vector spaces briefly. All right. We got about 3 more videos to go, so let's get to them.